Our first speaker is Thomas Andrillon from Monash University, and he'll tell us about wandering minds, sleepy brains, lapses of attention, and local sleep and wakefulness. Thomas, take it away.
Thanks, and thanks for the organizer for doing this amazing 24-hour conference. I realize that it must be quite late for many places around the world, so I'm very thankful if people are watching live or watching this asynchronously. So today I will be talking about mind wandering. So these instances when we're thinking about something else than the task at hand. And I will try to connect these instances of mind wandering, these moments where our attention lapses, with episodes of local sleep, of sleep intrusion, that will occur during our wakefulness. So it's a work that was done at Monash University in collaboration with now Tsuchiya, Genuines, and two very bright and dedicated students, Angus Birds and Tegan McKay. But I will start talking about this concept of local sleep. So sleep is classically defined as an all or nothing phenomenon. So either you're awake during the day and it is supposed that all your brain will be awake, or you're asleep and then all your brain will be asleep. This vision of sleep as an all or nothing phenomenon has been tempered a bit recently with the notion that sometimes your brain can actually display in different brain regions patterns of activity that are reminiscent of wakefulness or sleep. Typically during the day, that means that when you start getting tired, your brain regions start sometimes to get tired, and the most tired of this brain region can start display sleep-like activity while the rest of the brain is awake. And a similar phenomenon can happen during the night where part of the brain can wake up in a context of a globally sleeping brain. So how do this modulation of sleep-wake activity at the regional level affect the way we attend to or the external world? So to make this parallel between what happened at the physiological level and on the one hand, behavior, so the way we interact with our environment, but also with phenomenology, so the way we feel, the way we experience, we decided to apply a quite classical paradigm of sustained attention. So in this task, which involved 26 healthy adults, we asked participants to do the classical sustained attention to response task. It's a task where participants are in the digit version, which is a classical version. They are asked to monitor the appearance of digits on the screen that are presented in random order. And it's a classical go, no-go paradigm where participants are asked to press a button for all the digits except the digit number 3. So classical no-go, no-go paradigm, and with lots of goes and a few no-goes. We replicated this SRT in a slightly different version, including this time face stimuli, because we're interested in visual perception for some aspects of this task that I won't talk about today. So participants had to do the same kind of experiment where they had to press a button for all the neutral faces, and they had to withhold their response for smiling faces. So all the participants had to do these two versions of the task, which were intertwined in the whole session with 10 minutes blocks and breaks between these blocks. During a block, participants were interrupted from time to time in an approach that's called experience sampling, where they were asked about their subjective experience right before the interruption. And in particular, these interruptions were every minute or so. We asked participants to indicate whether they were focusing on the task before being interrupted, whether they were thinking about something else, so this phenomenon of mind wandering. We also included an option to report moments where they had the impression of not thinking about anything or not being able to recall anything. So a phenomenon of mind blanking, as if they will, the interruption will awake themselves from a state of blanking. So the idea with this task is that we're able to collect information about their behavior, their phenomenology and to make a link with the physiology recorded through EEG. And the third thing we did was to examine how much time they declared spending on task, mind wandering, or mind blanking. And we replicated a very, very common finding in the mind wandering literature, especially in the context of easy and undemanding tasks, is that participants reported being on task only half of the time. And as you can see, I mean, all the dots shown on the screen depict a given participant. There is quite a lot of variability between individuals, but on average, they were focusing on the time only 50% of the time, and the rest of the time they spend it either mind wandering 40% of the time or mind blanking. And the proportion of these states was modulated throughout the task. So mind wandering and mind blanking tend to increase block after block, and within a block we also see time on task effects. The state of the state of attention of these participants also impacted the behavior before an interruption. As I told you before, the task was a go-no-go with lots of goes and a few no-goes. And what happens is that participants get carried away, and they very often press a button during the no-go trials. And what we could see here is that when they declared being mind wandering, mind blanking, these instances of no-go errors were more numerous. What was more interesting was looking into the pattern of reaction times, because what we observed is that when people declared being in a state of mind wandering, they had the tendency to respond faster, as if they had become a bit more impulsive. And this could be related to their state of mind wandering. But when they were mind blanking, they had actually the tendency to slow down, as if they were in a state of sluggishness. And this has been interpreted in previous studies as mind wandering reflecting a state of high arousal. So you become a bit jittery, a bit more impulsive with your behavior and your own thoughts, and mind blanking being associated to a state of low arousal. However, when you ask participants about their vigilance, the subjective ratings of vigilance, we found that both mind wandering and mind blanking were associated with a state of low arousal. So it's not as if when they are mind wandering, they are feeling more awake, as if mind wandering was kind of a way to escape the boredom of the task. And these subjective ratings of vigilance were also confirmed by a more objective assessment of vigilance that was collected through the pupil diameter. So when recording the pupil size, which is a good proxy for arousal, we noticed also a reduction in both mind wandering and mind blanking compared to on state. So hinting to the fact that both mind wandering and mind blanking are reflective of a lower arousal state. So to dive more into this understanding of how a low arousal state could lead to both mind wandering and mind blanking, we decided to use this concept of local sleep to determine whether both mind wandering and mind blanking could be associated with this sleep intrusion. So these sleep intrusions are defined quite easily. So when you look at scalp EEG, they are defined as low frequency, high amplitude wave that are reminiscent of the kind of slow waves that are observed in non-REM sleep. We know from physiology invasive recordings in animals and humans that this high amplitude, low frequency wave correspond to episodes of neural silencing. And they are called local in the context of wake because they can happen in an isolated way. So you will see globally awake activity, and suddenly you will have such low frequency, high amplitude events, but they can also be local in space. You will see it in one electrode and not the others. How these were detected in practice was by taking the EEG, filtering the signal, detecting the negative peaks of these individual waves, computing the amplitude of each wave, and selecting the top 10% of this wave. So we are interested in certain frequency range and a certain amplitude range. This operation allowed us to select, in a rather arbitrary fashion, of course, these local sleep events. So now it's how this local sleep event looks like. in wake and what will be their correspondent in sleep. You can see that the temporal profile of these local sleep events is quite similar between wake and sleep, with some differences in the wake case. They are smaller in amplitude, of course, and they start with a theta component. But what's important here is this negative deflection that you can see that has been associated with this phenomenon of neuronal silencing. Now that we have detected this local sleep event, we can see whether or not state of mind wandering and mind blanking are associated with more of these local sleep events. And that's what you can show here. So these local sleep events are usually more predominant in central frontal areas. And you can see that in the case of mind wandering and mind blanking, we had more of this local sleep event. They had a higher amplitude and they were steeper, which is typically associated with a bigger local sleep event. Since these events are defined at the level of electrodes, we can use the detection of local sleep event for each electrode and see whether the detection of a local sleep event can be predictive of a given behavioral variable. And this is done at the single trial level. So for each trial, you determine whether or not it was associated with a local sleep event. And when you do that with misses, for example, you can see that misses can be predicted by the occurrence of local sleep event in the back of the brain, in sensory and associative areas, where false alarms were positively predicted by the occurrence of local sleep in the front of the brain, which makes sense given the involvement of frontal cortices in executive control. So what this result will indicate is that local sleep events can not only predict attentional lapses, but could predict the type of attentional lapses depending on where these events occur in the brain. If they impact frontal areas, you will become more impulsive. If they impact visual areas, you will become less able to process sensory information. And this is reflected as well in the reaction times, where local sleep in the back of the brain was predictive of a slowing down of reaction times, while local sleep in the front of the brain was predictive of an increase in reaction times. We could replicate these findings to a certain extent with the phenomenal reports of participants, and we observed that mind wandering compared to on-state was associated with higher amplitude event and steeper event in the front of the brain, while mind blanking was associated with steeper event in the back of the brain. So still indicative of this notion that consequences of local sleep depend on where it happens in the brain. And this result could be replicated using a modeling approach, using drift diffusion modeling. We could extract variables explaining the behavior, and we could again see this frontoparietal divide, where accumulation of evidence for ghost trials was reduced when local sleep was occurring in the back of the brain, and accumulation of evidence for no-go trials were also reduced. So here it's positive, but since it's a negative drift, this actually shows a reduction in the front of the brain. So what's important to notice here is that local sleep in the front and the back of the brain do not only differ by their location, but also by their spatial extent. So local sleep events in the back of the brain tends to involve more brain region, as you can show here. More neighboring electrodes will also show local sleep event. So it could be that the association between local sleep in the back of the brain and mind blanking could be related to their location, but the fact that also it seemed to be a larger event. So as a take-home message, I would like you to remember that when we get sleepy, we can observe this sleep-like activity in the brain, and it can be associated with behavioral lapses. And this local sleep event can predict your subjective experience and your tendency to mind wander. So if you're interested in know more about this, this has been published in a preprint recently, and I will be very, very happy to answer any question you might have.
Thank you, Thomas. That was really interesting and a lot of new concepts for me. So just from personal experience, it seems like, and I'll ask this question quickly and then we can go to the audience. It seems like the relationship between attention and sort of fatigue or local sleep, as I should call it now, is bidirectional. If I'm sort of sleepy, if I focus, then I can get my mind to sharpen and focus on the task. So is there evidence that the same networks are involved here?
So yeah, I mean, sleepiness is obviously something that we can modulate by being motivated, by being engaged in a task to a certain extent. So if you really sleep deprive heavily individuals, they will lose actually their ability to self-regulate their state and behavior. And I think this is actually related to the fact that one of the first regions to be impacted will be the prefrontal cortices. And what typically happens when you get really, really tired is that you don't even realize that your performance starts decreasing. So you wouldn't be able to monitor your own performance and say, oh, maybe I should refocus here. So it could be actually, it's actually very interesting to see how different brain region might be differentially impacted by local sleep. And sometimes the very mechanisms that are safeguarding us from fatigue will start to fail us because of this local sleep intrusion.
It's very interesting. Let's go to a question from the audience. Aiton is asking, you showed that the wake slow waves are strongest in the frontal areas. Can you be sure that they're not affected by undetected eye blinks or related other eye artifacts that maybe are confounding the EEG?
Yeah, no, that's an excellent question, because indeed blinks are important to take into consideration here, especially when we're tired, we tend to blink more. So we took a great care about making sure we were not detecting blinks as slow waves. So all these results were, for example, replicated during an ICA that are removing blinks. We are also detecting blinks and check that the timing of the blinks was not associated with the timing of the waves. It is important also to note that the shape of a blink artifact and the shape of this slow wave, the temporal profile will be very, very different. Usually blinks are a positive deflection of our frontal areas. So we're pretty confident that these are not blinks.
Okay, thank you. And we have a couple more questions.